This latency comparison chart highlights the mechanical advantage of in-memory caching. A traditional hard disk database query requires roughly 10 million nanoseconds to resolve. Routing that request through memory reduces delay to under 100,000 nanoseconds. Redis maintains this speed operating entirely within RAM, using a single-threaded event loop. Processing commands sequentially eliminates context-switching overhead typical of multi-threaded systems. To maintain high throughput, Redis employs asynchronous replication, where the primary node acknowledges writes before they reach every replica. This design prioritizes availability during network partitions, a trade-off that places Redis in the AP category of the CAP theorem. Inserting a fast memory layer in front of a relational database is only a partial solution. Without specific synchronization logic, the cache itself becomes a fragile single point of failure. When an unmitigated traffic spike hits an improperly configured cache, it offers no protection. Requests bypass it entirely, overwhelming the database, triggering total system collapse. Engineering a resilient system requires mapping application layer synchronization patterns, deploying algorithmic disaster mitigations, and configuring high-availability network topologies. High-performance caching at scale depends on the precise mathematical orchestration of how data is distributed across a network. In cache-aside, the application orchestrates data movement. On a read-miss, it queries the database, returns the value, and writes to Redis. For writes, it updates the database first, then deletes the Redis key to ensure the next read fetches fresh data. Deleting the cache entry before the database update creates a severe race condition. A concurrent read might fetch the old value from the database and write it back to Redis, leaving the cache stale until its next expiration. The write-back pattern prioritizes write speed. The application writes exclusively to the cache, while a background pipeline asynchronously flushes those updates to the database in batches. This strategy is designed for high-throughput workloads, like real-time analytics or IoT sensor ingestion, where immediate write acknowledgement is critical. The risk is data loss. If the cache node crashes before the background flush completes, any data that hasn't reached the database is permanently destroyed. The write-through pattern ensures consistency by forcing the cache to synchronously update the database before acknowledging the application's request. While this guarantees read-after-write consistency, it imposes a high-latency penalty on every write operation, as the system must wait for 2 storage layers to confirm. To prevent memory pollution, engineers use the write-around pattern. Database writes bypass the cache entirely, ensuring memory is only occupied by data that is actively and frequently read. These synchronization patterns determine the limits of a system's query latency, write amplification, and data freshness. Cache penetration occurs when requests for non-existent keys bypass the cache and strike the database directly. A Bloom filter mitigates this by acting as a memory-efficient gate, rejecting invalid requests before they ever touch the database. Additionally, caching null or default values for missing keys provides a secondary layer of protection against repeat requests for non-existent data. A cache avalanche occurs when a large volume of keys expire at the exact same moment because they were assigned the same time to live. This simultaneous expiration strips the system of its capacity, forwarding a sudden wave of traffic to the database that can lead to a cascading failure. TTL jitter prevents this by adding a randomized offset to expiration times. This ensures that key evictions are staggered over a wider window, smoothing the load on the back end. Database failures are rarely caused by simple traffic volume. They are caused by the synchronization of cache misses. A cache stampede happens when a single, highly popular hotkey expires, while thousands of concurrent requests are active. In the milliseconds before the cache is repopulated, every active thread will independently query the database to regenerate the exact same piece of data. The first offense is mutex locking, using the Redis setNX command, which stands for set if not exists. This forces only one thread to regenerate the cache, while all other requests wait or return a stale value until the lock is released. However, at extreme scale, the resulting lock contention can cause latency spikes that degrade the user experience for everyone waiting on that single key. Logical expiration addresses this by removing the physical TTL from Redis and embedding a timestamp directly inside the data payload. When a request finds a key that is logically expired, the system serves the old data immediately, while a background worker refreshes the cache without blocking any users. For ultra-high concurrency, engineers use probabilistic early expiration, driven by the xfetch algorithm. As the timeline approaches the TTL limit, the algorithm calculates a refresh probability that increases exponentially. This ensures a lucky request triggers a background refresh moments before the key actually expires. Effectively managing concurrency requires replacing fixed expiration windows with probabilistic regeneration logic. Once the application logic is secured, physical hardware limits eventually require a transition to distributed network topologies. Redis Sentinel provides high availability for datasets that fit within a single node's memory. A cohort of external Sentinel nodes monitors a primary master and its replicas. If the master stops responding, a Sentinel flags it as subjectively down. Once a quorum confirms the failure, it reaches objective down, electing a leader to promote the healthiest replica. To prevent split-brain scenarios during network partitions, the min replicas to write setting ensures the master only accepts data if it maintains a connection to its replicas. Redis cluster is required when dataset sizes or write volumes exceed the capacity of any single server. This architecture shards data across 16,384 logical hash slots distributed among multiple primary nodes. Clients use a deterministic CRC16 hash of each key to calculate the correct hash slot, routing requests directly to the shard hosting that specific data. Because requests are routed by slot, multi-key operations will fail unless engineers use hashtags to force related keys into the same logical hash slot. Scaling a caching layer involves a choice between the automated failover of Sentinel and the horizontal sharding of Redis cluster. This decision matrix provides a framework for coordinating Redis as an AP-optimized data store. Application layer synchronization patterns determine the foundational balance between data consistency and write latency. Algorithmic mitigations, including Bloom filters, TTL jitter, and xfetch, act as the primary defense against database overload. The final topology, whether Sentinel or cluster, depends on the physical requirements of your total dataset and write throughput. System resilience emerges from the precise engineering of how data enters, expires, and scales across the distributed network.